So the last thing in this section is dealing with the horizontal asymptotes for a rational function. And you're going to see those three cases that we talked about on that in that last video. You really can look at the degree of the top and the degree of the bottom. And I'm going to go back to where I wrote that down in the notes. So I'm looking here. If the degree of the top and the bottom is the same, the horizontal asymptote is the ratio of the leading coefficients. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. And if the degree of the numerator is larger than the degree of the denominator, you're not going to have a horizontal asymptote. So where does calculus fit into those rules? And that's what we're going to answer next. What we're really doing is looking at what happens as x approaches infinity or as x approaches negative infinity. So you're going to get the same result if you approach infinity or negative infinity for a rational function. That's always going to be a true statement. So let's look at what's happening in A. We're going to take the limit as x approaches infinity of 4x cubed minus 5x plus 8 over 2x to the fourth minus 7. There's a couple of ways to think about this. I'm going to use that idea that we just talked about with polynomials. So we know that a rational function is a polynomial divided by a polynomial. And we can use that idea that we talked about where we took the limit as x approaches infinity or negative infinity. And we really just looked at that first term, that leading term there, if you will. So if I look at that here, as x gets bigger and bigger, adding 8 is not going to do a lot to the problem, and subtracting 5 times that x isn't going to do much to the problem. So this numerator is going to be determined by what happens to that leading term, 4x cubed. So this is going to, instead of saying equals here, I'm going to say this is going to approach what happens when we take the limit as x approaches infinity. When we have 4x cubed on the top, and then if we treat the bottom the same way, well, as x gets bigger and bigger, subtracting 7 is really not going to do a lot to it. But that leading term, 2x to the fourth, is really going to determine what happens with that denominator. So now you see some things reduce here. First off, the numbers, the 4 and 2 reduces. That's going to leave us with a 2 on the top. And then the x's are going to reduce, and we're going to have an x in the bottom. So as x gets larger and larger, this whole thing is going to head to 0. So we would say that horizontal asymptote is going to be the line y equals 0 as x gets bigger and bigger. The same thing would be true if we were looking at approaching negative infinity. We would still approach the limit as x approaches negative infinity of those power functions for the numerator and denominator of the fractions. That still reduces. And so as x gets smaller and smaller and smaller, this is still heading to 0. If you think back to what your rule was in 171, we could get that answer the same way, couldn't we? We could say that I look at the degree of the top and the bottom. The degree of the top is 3. The degree of the bottom is 4. Because that degree of the bottom is larger, then that denominator ends up outweighing what's happening in the numerator over time. And that's what this process is showing you. That denominator is outweighing what's happening in the numerator, which means that this is heading to y equals 0. Now let's look at C. I'm going to look at the limit as x approaches infinity. So we could do that same concept. What's happening in the numerator is that everything is going to be really outweighed by that leading term 2x cubed. In the denominator, everything is going to be outweighed by that leading term 4x cubed. And if we think about how that reduces, that's going to reduce to a 1 over 2. Notice the x's are going to reduce there. And if I take the limit as x approaches infinity, I'm still just going to get 1/2. So we would say our horizontal asymptote is the line y equals 1/2. All those y values are getting close to 1/2 as x gets super big. It's also true as x gets super small. We would have the same concept, 2x cubed over 4x cubed, and then taking the limit as we approach negative infinity. That heads to the limit as x approaches negative infinity of 1/2, which heads to 1/2. So we get the same conclusion in both directions. Now I want to go back and look at B. So check out what's happening here. If we take the limit as x approaches infinity, the top is going to be determined by that leading term, 5x to the 6th. The bottom is going to be determined by the 2x to the 5th. So if we reduce, I'm going to have a 5x over 2. And those are just going to get larger and larger and larger. So we're heading to positive infinity there. And what that means is we have no horizontal asymptote. To have a horizontal asymptote, we're going to approach a specific number. Now, if we were to look at this, the limit as x approaches negative infinity, we're going to get the same conclusion that there is no horizontal asymptote. But this still reduces to 5x over 2. This would head to a negative infinity there. So all your rules that you talked about in 171 for end behavior and rational functions is really built on this idea of what's going on with limits as x gets super big or as x gets super small. So what I want you to get out of this section is that we can find end behavior and vertical asymptotes and horizontal asymptotes by using these ideas built in calculus with limits. Vertical asymptotes are where you're going to have that unbounded behavior. Horizontal asymptotes is asking the question, what happens as x gets really big or as x gets really small?